I want to address two questions that don't always pop explicitly to mind, but are in the background of every calculus student's mind. One is, these come up after, especially after you know the Fundamental Theorem of Calculus. After you've been using the Fundamental Theorem of Calculus to evaluate integrals for a while, you tend to forget that Riemann sums ever existed, the rectangle method, whatever you want to call them, and you tend to sort of have this idea that they were kind of useless. So the first question is, why would you learn about them? And second is, why would you use them when you actually know the fundamental theorem? So there's a basic conceptual reason about why learn about Riemann sums. I just want to address it briefly. And the answer is very simple. They are why integrals, including antiderivatives, actually apply to real life in, let's say, most cases. Maybe not all cases, but most cases. There will be lots of problems where it seems like a real world problem will be a sum of many small pieces. And something where you can break things apart, excuse me, apart into small pieces and then add them back up. And that is going to be a Riemann sum. In other words, you can write it essentially as an area problem and chop it up into rectangles and sum them back up. And it would be nice, well, we want to get the answer to that, basically. We want to get the answer. And so there's two versions of this. One is you use the theory of Riemann sums, the idea of Riemann sums, to realize that your problem is an integral, to set up the problem, to take it from, to sort of model it from the real world to math, and then you might be able to use the Fundamental Theorem of Calculus to turn it into an antiderivative problem. So that's the justification of why you would know about Riemann sums, even though the goal is to get to antiderivatives eventually. Okay. But the second question is, well, is there any time when you would use Riemann sums just directly in their own sake? Are they always just going to be this intermediary that you say, okay, I have some sort of real world problem, and I know I'm talking vaguely, but we'll talk about specific examples as we go. I have this real world problem, and I know that a Riemann sum tells me that an integral is how to set it up mathematically, but then of course I'm going to use the Fundamental Theorem of Calculus to turn it into an antiderivative problem and be able to get the answer. Well, turns out that's not always the case. Just one more, let's see. Now that's enough on the abstract problem, sort of the conceptual problem. Let me turn to the concrete problem. Why would you use a Riemann sum directly? Why would you actually calculate it out? Well, suppose we want the area. Let's go to the problem we know is modeled by Riemann sums. Let's say the area under y equals, I'm going to use the most famous example. I'm not going to try anything particularly slick here, from x equals 0 to x equals 1. Turns out this is a really, really important thing to know. For example, probability in statistics. It's the most important function, in fact, in probability in statistics, and one of the top 10 and most important functions in the universe. Okay, so there's lots of places where you need this: physics, all kinds of places, chemistry, thermodynamics. But maybe let's say probability in statistics is the first place people would often encounter it. Well, what does this function look like? It's a hump function. It's different from hump function, the hump function that I was talking about in another video, but it's not that radically different. It's biggest in the middle, and then it decays pretty darn quickly at the ends. And if we wanted to get this area under this hump from 0 to 1, that's what we would be doing here. So if we used the fundamental theorem, let me delete that to give us more room. If we use the fundamental theorem, we'd write it as the definite integral from 0 to 1 of e to the minus x squared dx. And in these videos I still haven't explained where the dx comes from, but if you're watching this coming from somewhere besides my class, you might already have an explanation of that. So this means can be interpreted in two ways. One is it's just a notation for the area under this curve. Or it's an instruction to go ahead and take the antiderivative, let's just call it f, of e to the minus x squared, and evaluate it at 0 and 1. That's just a notation for f of 1 minus f of 0. Oh, nothing could be easier, as long as I can find a formula that whose derivative is actually e to the minus x squared. And that's where it comes to a crashing halt. There is no formula for f. It exists. The function exists. But you can't write down a formula using any of the algebra, exponentials, e's, sines, cosines, tangents, inverse tangents, whatever. You can prove that there is no such formula for that. It's called not being an elementary function. And so that's going to be a problem where this comes to a big old crashing halt. You can't use this method, even though you can formally write it down. It's not going to give you anything. It's not going to give you the number. So instead, we have to go back to the totally different way. The limit as n goes to infinity of an actual sum, not one of these stylized s's, but an actual Greek, good old-fashioned Greek s, thousands of year old, I guess, of, okay, now let's see, what do we need to do? We need to set up a little bit more. We need the delta x is going to be b minus a, which is 1 over n, okay, and so x sub k, I picked a simple example, it's 0 plus k delta x. Let's use the right endpoint method just to be simple, which is going to be k over n. Okay, so do I just put that in here? Here's a big mistake people make. Ta-da, done. There's something big missing here. What's missing? Can you figure out what's missing? The function. These are the x values for the rectangles, but I need to get the heights of the rectangles by plugging them into the function. So I need e to the minus, stick that in there, that squared. And then I need times the delta x. I'm going to put that in front. And so that is how you would have to calculate it. Well, no, but can we take that limit? Well, unfortunately, we can't take that limit exactly. We don't know how to take that limit exactly. We have to actually go back to the approximate version. It's approximately, well, pick a big number. Let's say 1,000. Now, this is not something, oops, you're going to want to do by hand, but that's okay. If you've got a seemingly impossible problem, it's not exactly a shame to have to use a calculator as long as you actually can solve the problem. And it turns out that's a pretty good estimate for this magic number, the integral, the area under this humpy curve, the bell curve, the Gaussian, whatever you want to call it, the normal distribution, lots of names for it, from 0 to 1. And that's how you would actually do it in practice, although there's more sophisticated methods, but that's really the idea. It'd be wonderful if we could do it this way. We're going to do a lot of examples of functions where we can do it that way, but this won't work that way. So even if you know FTC, you actually do have to end up having to do this quite a bit. I'll say that to do it better, we could do the midpoint rule, which would be better. The trapezoid rule would be similarly good answer to midpoint, but not a lot better. Maybe probably not even as good. There's something called Simpsons Rule, which you learn in BC or in other calculus classes. And there's some elaborations of that as well. But they all really come off this basic idea. They don't really come up with really super new ideas.